In last class what we have seen that what is a clean room, right, safety protocols while entering the clean room. We will also share a video with you of how to access the clean room, and we have also kind of seen that what not to do, right, in particularly when you use different chemicals and classes of clean room according to ISO standards. We also understand that class 10,000, class 1000, class 100, class 10, how the clean rooms are identified, isn't it. Now in this class what we need to understand is what is the substrate and how we can grow silicon dioxide if the silicon is our substrate. Again with an understanding of a system, a biomedical system, and if I am reiterating, then these chips will be integrated into this biomedical system, and finally we will understand the mathematical aspects of how this biomedical electronic system design would work for that, right. So silicon dioxide. Now when you want to have a silicon dioxide, this is the process that you start with a metallurgical silicon, or you start with a sand which is silicon dioxide. You have to purify it to 99.999% pure, actually 99.9 times 9% pure, and then you can go for a once you go for a technique called CZ technique or Czochralski technique or FZ technique called float zone technique, you can fabricate different silicon wafers. But through CZ and FZ you are only able to get the polycrystalline silicon ingot, which you can see here, right. Either CZ technique or FZ technique, and once you have that you get the silicon ingot. Once you have silicon ingot, you have to go for dicing, sawing, polishing, and it can be chemical mechanical polishing, or it can be and followed by lapping, right, and followed by chemical etching, and then finally you will get the silicon wafer. Either it can be single side polished wafer or it can be double side polished wafer. Now what do I mean by single side polished wafer and what do I mean by double side polished wafer? If you can see the wafer that I am holding in my hand, you will understand the difference. Can you see the wafer that I am holding in my hand? Yeah. So as you can very clearly see, this is the polished side, so you can see the reflection, right. If I just do this, you can see the reflection, isn't it. But if you see the back side of the silicon wafer, this is rough, isn't it. See, it's rough. Front side polished, back side rough. Front side polished, back side rough, right. This is single side polished wafer. If I have double side polished wafer, means front and back both will be polished, right. So this is what I mean by single side polished wafer. If I go to the next slide, silicon, as we all know, right, silicon bowls and wafers, you have to if you see this picture, you will understand that the silicon bowls are made in a class 10, class 100 kind of clean room environment. It's called foundries, silicon foundries, and then the wafers are cut from the bowl, which is right over here, right. And the reason of fabricating this particular bowl inside the clean room is to make sure that there is no contamination. So a silicon ingot or bowl is what we say. CZ technique, as you can see here, it is also called Czochralski technique. Depending on the pronunciation, you will understand through different videos. Czochralski is pronounced in a different way. However, the important thing is it's a most important method for production of bulk single crystal silicons. Also, it is cheaper than FZ technique. At the beginning of this process, the feed material is put into the cylindrical shaped quads. You can see this particular schematic, right, here, right, and what you see that the external material, right, all the way the external material is made up of what. So the blue color thing, right, that is a water cooled chamber. Then you further go in, you will see that there is a heat shield, right, and you further go in then you will see there is a carbon heater, right. So then in further there is a graphite crucible, right, and then there is a quartz crucible, graphite crucible, quartz crucible. Then the bottom is crucible support, there is a spill tray, and then there is a electrode for the heater, right. Electrode is here, and you apply voltage between these two electrodes, and you can heat the heater. Very simple, you all know, right. Heater is nothing but the resistance is given by rho L by A. Depending on the length and area, you can change the resistance of the heater. Resistivity for a given metal remains constant. So what we do here is that you start with the seed crystal. Now let me just rub it down. So and you can see here there is a seed crystal, right. So there is a seed crystal at the top in this way, and when you, and this is a molten silicon, right, molten, which is molten silicon. So, when I dip this rod or seed crystal inside this molten silicon and rotate it, so you can give one direction rotation, or and this crucible which is holding the molten crystal will rotate in a opposite direction, right. Seed will rotate in one, crucible will rotate in opposite direction. So, if a seed is rotating in clockwise direction, the anti-clockwise direction, the crucible will rotate in a clockwise direction, or vice versa. Now, depending on the orientation of the seed crystal and depending the pulling rate and the rotation rate, the thickness of this bowl would be different, right. So, that is something that we need to understand. This is what this Czochralski technique is all about. If you read further, it says that at the beginning of process the feed material is put into the cylindrical shaped quartz, which is right over here, right. Once you place the material, then you have to heat the material. This crucible is graphite crucible with a fused silica lining and is melted by resistance or radio frequency heaters. After you fed the material is completely molten, a seed crystal is introduced, right. Seed crystal from here is introduced, and from the top into the free melt surface, and a small portion of the seed metal is, or seed crystal is dipped into the melted zone or molten silicon. Then the seed is slowly withdrawn, right, slowly withdrawn from the melt, right, under rotation. I told you, right, either you have to rotate in this direction or you can rotate in the opposite direction, clockwise or anti-clockwise. And during the growth, the diameter is controlled by carefully adjusting the heating power, pulling rate and rotation of the crystal, right. Three things is very important, or three things are very important. One is the heating power, second is pulling rate, and third is the rotation of crystal. So, through this technique what we get electron grade silicon. And why we are understanding this technique? Because finally we will use silicon wafer to fabricate different devices. So, the seed crystal is pulled at an optimized rate that minimizes defects, because faster you pull, more defects you have. If it is very slow, again you have problem. So, you have to optimize the rate at which the seed crystal is pulled out of the molten zone. You can get a constant ingot diameter if your rate is optimized, the pulling rate is optimized. Impurities, both intentional and unintentional. If it is not impure, you all know silicon becomes amorphous. Silicon is a intrinsic silicon. If you dope it with N type or P type, it becomes extrinsic silicon. So, intentionally you can dope, or unintentional there is a doping which are introduced. Dopants are impurities are introduced into silicon ingot. Intentional dopants are mixed into melted during the crystal growth, while the unintentional impurity originate from several things including ambient environment, crucible, etc. This all have all impurities have different solubilities, and an equilibrium segregation constant Ko. If you want to define an equilibrium segregation coefficient Ko, it is given by Ko equals to Cs by Cl, where you can say that Cs is the equilibrium concentration of the impurity in solid, while Cl is the equilibrium concentration of impurity in liquid, right, at the interface. So, Cs by Cl is Ko, and Ko is given as Ko is known as equilibrium segregation coefficient, right. So, important thing, remember Ko equals to Cs by Cl. The impurity is segregated into the melt, and melt becomes progressively enriched with impurities as the crystal is being pulled. Now, this is a video. Let me play the video. This shows it from TU Delft. It's very informative video for academics. So, we will see here how the crystal is grown. Okay, so now you have seen, right, how the technique works. Now it becomes very easy for you to understand that how this easy technique is used for growing the ingot, and finally from that ingot we fabricate several wafers. Now let us go to the another technique which is called float zone. The name itself suggests that there is a floating zone. So, float zone is based on the zone melting principle and was invented by Theurer in 1962. Schematic of the setup is shown right over here. Here you can see that there are two things. One is a the top one is a polycrystalline ingot, and the bottom one is a grown single crystal material that grows here in the bottom, right, and you have a single crystalline seed at the bottom. Whatever the molten zone is created is from the seed crystal to the growth crystal. So, it is right over here, right, here it is heated using RF coil, and this is a molten silicon. So, if you read it, it shows the same thing, that the melt zone is established between lower seed material and upper feed material. The upper one is called feed material, the lower one is called seed material, right, seed material. Alright. By applying localized heating. Where is localized heating? Right in the interface. The floating zone is moved along the rod in such a way that the crystal grows on the seed. So, when the feed crystal is moved and the floating zone is moved such a way that this seed crystal that you can see here, it starts growing in this direction. And simultaneously melting the feed above the floating zone. So, when it starts growing in this direction, as we have seen, this feed crystal starts melting further, right, because you get the seed crystal from the feed crystal. The second material as well as the feed rod is supported, but no container is in contact with the growing crystals or the melt, which is held in place only by surface tension. This whole thing is held only by surface tension, and the good thing is that because of this, impurities into the molten zone tends to stay in the molten zone rather than be incorporated into solidified region. That means that the quality of the wafer that you get using FZ technique is way better compared to the CZ technique. In fact, a very pure single crystal region to be left after molten region has passed due to the difficulty in growing large diameter. See, the difficulty of FZ technique or limitation of FZ technique is that you cannot grow a larger diameter of silicon wafer, and that is why FZ becomes more expensive. But however, FZ crystals are preferably used when there is a low oxygen concentration requirement, right. Let us see again important informative video from on the FZ technique. Let me play it. Okay, so you have seen, right, now what you have seen a CZ technique, you have seen FZ technique. Now let us see in a schematic. If you start with a crucible, you start putting the polysilicon and you melt it, right, and what is the process to all the way to bring the wafer. That means right from the start to the end, what are the process involved. Let us see this one by one. If you see the schematic, what you see is that polysilicon is added to the crucible, and there is and then it is heated either using RF or using the resistive heating. Then you can introduce a seed crystal. Here the seed crystal is introduced into the molten zone. When you do that and you pull it at a constant rate or at with a different time, then what you get is a single crystal ingot. Once you have this, you have to trim the sides, right, this side and this side you are trimming it. Then you have to create a flat zone or flat grinding. There is a reason of flat grinding. Every wafer that you see would have this flat grinding, and a flat grinding on the wafer will always be seen visibly like a circle. This is a flat grinding, right. For silicon wafer, this is a flat grinding. You take any silicon wafer, you will see a flat grinding on one side, and sometimes you have a small flat on the another side. The bigger flat, right, is called primary flat. The smaller flat is called secondary flat. Flat, 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 right, because this is a flat. When you flat grinding gives us a flat. So, this flat grinding helps us to get the primary flat in all the silicon wafers, primary flat in all the silicon wafers. Depending on the primary flat, the angle of secondary flat with respect to primary flat, we can say it is 100 or 111 or 110. We can also understand whether it is P type or N type. Thus, the flat grinding is very important step. After you do that, you can slice the wafer. I will just show you in the next slide using diamond wires, and then there is a edge rounding followed by lapping. This is a lapping process, right, and then there is a wafer edge followed by polishing. After you polish either both the sides, you get double side polish wafer. If you polish same side, only one side, then you have single side polish wafer followed by wafer inspection. So, these are the steps. If you just repeat, then the crystal growth is given as once you melt the polysilicon in crucible, next is create a ingot, next is trim the the sides of the ingot, then you do flat grinding followed by wafer slicing followed by edge rounding, lapping, etching, polishing and wafer inspection. Now, Once you do that, you see here there are two schematics you can see here, right. One on the left side shows the diamond coated wire, and this there are two reels where there is a take up reel, there is a wire guides, and there is a wire moving in a direction. This is a silicon ingot. So with diamond wires you can slice, you see here the diamond wires, you can slice the ingot into many wafers, isn't it. And then once you have this sliced wafers, you do the lapping and polishing. So this is again a video, you just see how it works and what is the reason of using a thin wire, because in this you know, right now with the technology that we have, even a few microns has a lot of thousands of transistors. So if we waste a lot of silicon at the during the fabrication, that's in fact a loss in the total amount of material that a company has to bear, and that is a very high loss. And that is why to remove this loss, or to reduce the amount of silicon that you have to throw it during this fabrication, you use this process of slicing the silicon wafer using diamond wire. So I will just play the video and then you can see the next slide. So now you have seen this slide, right, and now what you see is that after this the important thing is why we have studied all these things like silicon fabrication, silicon dicing, slicing, lapping, polishing. All this thing is because 95% of the transistors devices are still made using silicon wafer, and that is why important to understand how silicon is fabricated. In the present course, Professor Chandramani will talk about the mathematical modeling, where he will talk about the biomedical system, and there you will see that this biomedical system has an integrated chip which is made out of silicon, and that is why the reason of learning silicon at this point of time. So crystalline silicon is the hard and brittle material that deforms elastically until it reaches its yield strength, and tensile strength is about 7 gigapascal. Young's modulus you can see is near that of stainless steel. Mechanical properties are uniform, good thermal conductor, and mechanical integrity up to 500 degrees centigrade. So these are some of the important things of silicon material. Now very important understanding is Miller indices, which was developed by William Miller in 1839 and are used to specify direction and plane in the crystal. So as you can see, just read this particular slide. Let me go to a very important slide which is in one or two lines. Anyway, one or two slides you will see here A, B, C are the edge lengths, alpha, beta, gamma are the interaxial angles, right. You can see here alpha, beta and gamma. A, B, C are edge lengths, and then you have A, B, C are inverted to find HKL plane. I will just show it to you. And negative expressed with bar are A bar, B bar or C bar. This kind of bracket, right, is represented as single planes, while the curly brackets are representing the family of planes. So here you can see HKL plane or HKL represents a plane. Here HKL represents a single point. If you have curly, then family of planes. If you have square bracket, then represent as direction, while in this case if you have HKL between two arrows, represent a family of directions. So it starts like plane, family of plane, direction, family of direction. But even important point is the crystallography planes, and here from the planes itself you can understand the crystal orientation and the whether it is p type or n type. The Miller indices are very important to understand all these things, like for example 111, 100, 111, 100. Why it is 111, how it is 100, how the crystals are oriented and what are the planes. This Miller indices helps to understand this all points. However, for this course you do not have to worry about it. Let us focus more on what is important, which is identifying the wafer based on the flat that is present on the silicon wafer. Now here you can see that there are flats, one primary flat in every silicon wafer. You can see, let us name it as 1, 2, 3 and 4, right, and here you can see there is a primary flat. We will say primary flat as a PF. Here also there is a primary flat. In this case also you find primary flat, and finally in the fourth one also you find primary flat, isn't it. Now you see that where is the secondary flat, okay, is in this case can you see secondary flat? You cannot see. In this case, yes, I can see a secondary flat right over here, isn't it. In this one, yes, secondary flat is here. In this one, yes, it is right over here, correct. Now this is 90 degree with respect to primary flat. This is 35 degree or 45 degree with respect to primary flat. This is 180 degree with respect to primary flat, isn't it? So, depending on where is the angle of the secondary flat with respect to primary flat, you can say it is a p type material or is a n type silicon wafer, and whether the orientation is 100 or 111, right. We have seen what is the meaning of this particular thing is a family of directions, right, represent a family of directions. So, single processing wafers, you can see here, once it is finally processed, they is called single die, and each single die has billions of transistors which are used for several applications, and in a foundry it takes several weeks to pass a lot, and the location of an IC on a wafer is called a die site. A flat on the wafer is used to a reference plane to form a grid for die placement, and the number of wafers tests per week indicates the manufacturing capability of the chip factory. Depending on the size of the wafers, again the wafer is generally on the diameter, you see a diameter. So, when I say 1, 2, 3, 4, 6, 8, 12, 18, I will say that is a diameter of the wafer that is there, right. It is 4-inch wafer, or it is a 6-inch wafer, or 12-inch wafer, or 8-inch wafer, it depends on the diameter of the wafer. With respect to diameter of the wafer, the thickness of the wafer also changes, right. So, for let us say 4-inch wafer which is 100 millimeter in diameter, the thickness generally we can obtain is right from 200 to 1000 microns. Generally we use 500 micron thick 4-inch wafer in this department. Again same process, just in a different format. What you see is a CMP or double side polished or single side polished. CMP stands for chemical mechanical polishing, and what you get is a smooth surface, either single side polished or double side polished. Single side polished wafer are cheaper compared to the double side polished wafers. Then there is a edge countering, and therefore edge countering, the edge roughness, edge surface roughness, edge geometry is very important. Rounded or blunt shape and bullet or beveled shape, as you can see here, what you see is edge blunt rounded, and here is a edge bullet shaped. So, this is the different way of edge countering. Again we will not, you do not have to bother about why it is blunt needed, rounded, or you require a blunt bullet shaped or bevel shaped edge, okay. But what you need to understand is that in chemical mechanical polishing is used for smoothing of surface or smoothing of surface, chemical etching with abrasive polishing, and generally aluminum, C or silicon nanomaterials are used for polishing the wafer. Now, when you get a silicon wafer, right, and you want to start the process, the first step is the RCA cleaning. RCA stands for Radio Corporation of America. There is RCA 1 and RCA 2. This is a two-step process to remove the particulates, organic and metal contamination, and also to remove the organic contamination and particulates. So, the RCA 1, you have to take a 27% of NH4OH in the ratio of 30% H2O2 in the ratio of H2O. That means 27% NH4OH is to 30% H2O2 is to H2O, which is 1:1:5 at 75 degrees centigrade for 10 minutes. You have to dip the wafer in this kind of chemical, right, and finally this will help in removing the organic contaminants and particulates. You take it out, rinse it with DI water, and you can dip it in another solution which is 70% HCl is to 30% H2O2 is to H2O in 1:1:16 1:1:6 ratio. I am sorry, in earlier one also I may have wrongly mentioned as 1:1:15. It is 1:1:5. In this case, this is 1:1:6, and the temperature is 75 degrees centigrade for 10 minutes. So, RCA 1 and RCA 2 are two steps. Finally, you have a HF deep cleaning, which is 49% HF into is to H2O is equal to 1:50. This is 1:50. So, when you perform this, then the wafer becomes cleaner. Now, does that mean wafer is not clean? It is already clean, but you have to clean to make sure that there are no organic contaminants and there are no metal contaminants on the wafer, otherwise that will affect the overall characteristics of your device. There is another video, let me play it again, very informative video to see that how the silicon wafer is fabricated, how the process flows are there, and you will see that in most of the things that there is a very less involvement of the engineers. It is more like an automated system to minimize the contamination during the fabrication, okay. So, I will just play the video. Alright. So, you have seen now how the silicon is fabricated in a foundry. Let us quickly see the effect of silicon dioxide. When you have silicon dioxide, the wafer will look different than what is a silicon wafer, right. So, if I hold the wafer which is in right now in my hand, you will very clearly see that if it is a silicon dioxide or silicon, you can see this wafer, right, it is silicon, and you can see this wafer, it is silicon dioxide. You can see the change in color, right, compared to this one, there is a change in color in this one, isn't it. See, there is a change in color. So, this one is there is a silicon on which we have patterned our material, this is silicon dioxide on which we have patterned the material is metal. There are two different patterns that you do not have to worry. The point that I am making here is that the silicon wafer that you am holding here, if you directly deposit a metal, in some cases it will not work because it will get short circuit and or the effect of metal directly on semiconductor, you know, right. If you have studied physics, you understand the work function and other things. However, if you use oxide, then it is an insulator material, and thus the silicon is only used as a base material. The entire thing that we grow on the silicon will be our device, including the substrate of course, but there is a insulator material. This insulator is generally a silicon dioxide. Now, silicon dioxide in this case is just an insulating material, but when you create a MOSFET, right, or you create any other device, then as you can see in the schematic, you will see that it can be used as a filled oxide, it can be used as a masking oxide, it can be used as a pad oxides, gate oxides, chemical oxides for native oxides which is about 1 nanometer, it can be used as a backend insulators, it can be used as a masking oxide. So, let me again tell you what exactly all these things are. 1 nanometer is when you keep the silicon wafer in room in a environment which is a lab environment, right, because of the presence of oxygen, there is a native oxide that is created which is close to 1 nanometer, and the way to remove this native oxide is by dipping this wafer into BHF. BHF stands for buffer hydrofluoric acid, buffer BUFFER, hydrofluoric acid, that you know, right. So, if you dip this silicon wafer which has a thin layer of oxide into BHF, right, then the oxide will get etched because BHF is a etchant for silicon dioxide, is a etchant of silicon dioxide, alright. So, that is your 1 nanometer oxide. Then you talk about gate oxide, gate or tunnel oxide. Those who are from electronics background, they would know that in case of MOSFET, right, generally what we learn is there is a source, there is a drain, and there is a gate, right, and then in the gate there is very thin layer of oxide that you have, isn't it, and then in this one you have a thicker oxide, right. This is your silicon dioxide, silicon dioxide, silicon dioxide, silicon dioxide, and this one is also silicon dioxide. Okay. On this you have your metal contact pad, N plus P, this is your gate, this is your source, this is your drain, right, this is contact. I am just showing a very basic view of the MOSFET, right. So, it is a NMOS because the channel is through the N plus region, and then here there is a thin layer of gate oxide, right. This gate oxide thin layer is about 10 nanometer, and we are just understanding depending on one of the technology. There are different technologies to fabricate MOSFETs. This thin layer of gate oxide is grown using technique called thermal oxidation. And thermal oxidation, we can have dry thermal oxidation or we can have wet thermal oxidation, dry oxidation or wet oxidation. Okay. Okay. Now, let us go to the next step. Next step is your 0.1 micron masking oxide. What does masking oxide mean? Okay. Let me give you an example. You have a silicon wafer, alright. What I want is I want to etch silicon wafer like this, etching, ETCHING, right. I want to remove that silicon wafer, this much silicon from my silicon wafer. This removing of silicon material from the silicon wafer is called etching of silicon, alright. To do that, if I dip I know that what is the chemical that are what are the chemicals that can etch silicon. Suppose I know that potassium hydroxide KOH, if I dip the wafer silicon wafer into KOH, it will dissolve. If I dip this wafer, let us say in a beaker like this, which is full of KOH material, right, what will happen is, this is a cross section of silicon, right. I will see that the silicon starts dissolving, this remaining area will dissolve, only this much area is left. If I dip this for long time, this also goes away, so everything is dissolved. So I do not want that, right, I want only to the silicon should get etched only from this region, for remaining region silicon should not get etched. So what should I do? To do that, what will I will use silicon dioxide. I will grow silicon dioxide. I will tell you how the silicon dioxide is grown in one of the class. This is a silicon dioxide, this is silicon dioxide, this is silicon. Now you understand silicon dioxide will not get affected in in KOH. Silicon dioxide in KOH, which is potassium hydroxide, silicon gets etched, right, it is a HN for silicon, is a HN for silicon, but KOH will not affect silicon dioxide. That means if you dip the wafer with silicon dioxide, like if you dip this wafer, silicon will not get etched at all. So what you do is you perform a photolithography and you remove oxide from the top in this way to create a window. You see, you perform photolithography, we will see photolithography in one of the class, silicon dioxide, silicon, right. So I perform a photolithography to remove silicon dioxide from this particular area, so that we can say that this is a window that we have created through which we can see silicon. Now if I dip this wafer in KOH for known amount of time, what will happen? I will have my silicon dioxide as it is, because silicon dioxide will not get affected in silicon etchant, we already know. This is silicon dioxide, right, and here you can see that silicon is etched, That means that silicon dioxide, my silicon dioxide acts as a mask, that is why it is called masking oxide. That is why it is called masking oxide. Finally, field oxide, just we have seen in case of MOSFET, it is 1 micron thick silicon dioxide, right, that is used for as a field oxide. So the same thing is you can see in the schematic that if I have silicon dioxide and if I dip in a HF, then HF is a HN for silicon dioxide, and that is why the silicon dioxide is etched. But if I dip this wafer into the silicon etchant like KOH or TMAH, then silicon will get etched from the back side, but from the front side it will not get affected, because silicon dioxide acts as a mask. So when it acts as a mask, is not only mask against the silicon etchant, but it can also act as a mask of not allowing the dopant to pass through. That means in this case what you see, if I have a silicon wafer, right, and I want to dope silicon wafer only in this region, suppose it is p type silicon wafer, I want N plus dopant only in the center of the silicon wafer. What can I do? I will take a oxidized silicon wafer and then I will again remove the oxide from the center, and remaining all the sides I will keep oxide, as you can see here, top and bottom, and then if I dope this silicon by N type dopant, right, then there is a two ways of doping silicon wafer. One is called diffusion, one is called ion implantation. Diffusion and ion implantation. Okay, ion implantation. So when you do diffusion and ion implantation, this dopant that you are doping cannot pass through silicon dioxide, thus again in this case silicon dioxide acts as a masking oxide. The silicon dioxide acts as a selective mask against diffusion at high temperature, because the DSiO2 is extremely low, less than D silicon. As we know, right, oxides used for masking are about 0.5 micron to 1 micron thick, and in this case what you can see is there are different dopants and the diffusion constants at 1100 degrees centigrade. The diffusion constant of silicon dioxide is extremely less than diffusion constant of silicon. That is what I said about DSiO2 less than DSi. In this chart what you see is, if I want to use silicon dioxide for as a mask for boron and phosphor, then how much should be my thickness. So from here if I use boron as a dopant, right, into a silicon wafer, then if I am using a 1200 degree centigrade temperature, then I have to draw like a line like this, and then depending on how many hours, right. So if I say that I am doping my boron for about 1 hour. So if I dope my boron for about 1 hour at 1200 degree centigrade, I require 0.05 micron thick silicon dioxide. This is what it says. This chart shows like this. Okay. Suppose you said no, I want to dope phosphorus into silicon for how much time? 1 minute. At what temperature? 1200 degree centigrade. Then you can continue here and you can see that approximately what is the thickness? 0.8 to 0.9 micron thick silicon dioxide can act as a good mask for to not allow the phosphor to enter silicon. That means if I have silicon wafer here and if I grow silicon dioxide like this, this is silicon wafer, and I want to diffuse phosphor into silicon wafer, then this silicon dioxide, if the thickness is close to 0.9 micrometer, this dopant, which is your phosphor, will not pass through silicon dioxide. The silicon dioxide acts as a mask against the dopant and protects the region which is below it. That means in this region you will not see dopant, but in this region which is there is no silicon dioxide, you will see that there is a phosphor doped into silicon wafer. Same thing is here, right, and there is a dry oxidation, wet oxidation. Let us see this dry oxidation, wet oxidation in the next class, followed by lithography and followed by some of the examples how you can fabricate different chips that can be used for biomedical applications. Till then, you take care, have a nice day.